This will be our last video lesson for this unit, and we're going to add another important rule to live by that will help us differentiate these rational functions. Rational functions have a lot going on. There's a function on the top and a function on the bottom. The function on the top can tell us where the x-intercepts are going to be. The function on the bottom can tell us about the vertical asymptotes or where those are going to be. We can use the number at the end or those constants at the end of both functions on the top and the bottom, the numerator and the denominator, to determine the y-intercepts. And we can figure out the horizontal or oblique asymptotes by using the largest term in the numerator and the denominator. And just as a quick reminder of how that works, because that's actually something we're going to be looking at a little bit later in this lesson, is tying all of this horizontal, vertical, oblique asymptote stuff together to graph these rational functions. So just as a reminder, when we have a rational function, we want to take a look at the degree of what's happening both in the top and the bottom. So if the degree in the top is equal to my degree in the bottom, we're going to divide the coefficients of the top and the bottom to find the horizontal asymptote. So in this example here, they have different degrees. But if they did have the same degree and it was 4 over 1, then I would take 4 over 1, and that would tell me that my horizontal asymptote will be where y equals 4. If the top has a less of a degree than the bottom, then my horizontal asymptote will be at y equals 0. But if my degree at the top is greater than my degree on the bottom, could be a couple of things happening. There could be no horizontal asymptote at all, or if the top is greater than the bottom by exactly 1 degree, then we're going to have an oblique asymptote. Now, an oblique asymptote, for those of you, if you don't remember, is just a straight line that's not going to be parallel to the axis that the curve approaches. So you've seen these in grade 11. You would have seen these in last semester in functions. So they occur in rational functions in which the degree of the numerator is greater than the degree of the denominator, or our top is greater than our bottom. And they can be found by dividing the polynomials. Now, dividing those polynomials means either synthetic or regular polynomial division. And as if that wasn't enough moving pieces, that's a pretty big moving piece. If you don't remember how to divide polynomials using either one of those methods, synthetic or regular long division, then I'm going to post a couple of links to a couple of videos on the VLE just as a refresher or a reminder, but I'm not going to take the time during this lesson to go over that. So when we're working with rational functions, it's a lot like skateboarding down a ramp while carrying a cup of water and trying not to spill it. Not only do you have to balance yourself, but you also have to control the water to make sure that it's not going to spill. So like I said, there is a lot going on with rational functions. So let's start by looking and graphing an example. Let's find all the asymptotes of this rational function. We have y equals 2x squared minus 1 on the top over x plus 1, and then sketch the function near those asymptotes. So remember, this is nothing new. We've been doing this for a while now. We are going to start by figuring out the vertical asymptotes. We're going to look at the limit of the functions as it's approaching that vertical asymptote, and then we're going to take a look for any horizontal asymptotes. So let's start with the vertical asymptotes. So we have a vertical asymptote, and remember, it's the bottom of our expression or the bottom of our function that's telling me where that asymptote is going to be, that vertical asymptote. So we have a vertical asymptote when x plus 1 equals 0, or when x is equal to negative 1. So now we know that we need to figure out what's happening as this function approaches negative 1 from both the left-hand side and the right-hand side. So our limit as x approaches -1, let's do the left-hand side first, and let's use a value that's close to that from the left-hand side. Let's use -1.01. So let's plug that in. We have 2 times -1 squared minus 1 all over -1.01 plus 1. That gives us 2 minus 1 all over -0.01, which is going to give us -100. So recall that if this is a negative value, that means that as this function approaches that asymptote at -1, then the function itself is going to be approaching negative infinity. Now let's take a look at what's happening if we're approaching it from the right. So my limit as x approaches -1 from the right-hand side. And now let's use a number really close to that right-hand side. Let's use -0.99. And we have 2 times -1 squared minus 1 all over -0.99 plus 1. That is going to give us, again, 2 minus 1 on the top. But this time on the bottom, we have a positive 0.01, which is going to give us positive 100, which means that my function is approaching positive infinity as it's approaching this line, as it's approaching this asymptote. Now we have to deal with the horizontal asymptotes. So those were my vertical asymptotes. Now let's think about these horizontal asymptotes. So when I'm looking at the horizontal asymptotes, I'm comparing what's happening between the leading terms on the top and the bottom, and I'm looking at the degrees. So I have a second degree on the top. So I have a second degree on the top, and I have a first degree on the bottom. So that is telling me that my top is greater than my bottom. 2 is bigger than 1. So there's a couple of things we could be thinking about here. We could initially say that that would be no horizontal asymptote, because that's kind of what we've been thinking about up to this point. However, this is greater. It's 1. It's by 1. It's off by 1. The top is bigger by 1, is what I'm trying to say, than the bottom. Therefore, there must be an oblique asymptote. So this is where we need to figure out, well, where is this oblique asymptote going to be? We're going to need to use the top of that function. We're going to have to divide it out because we need to factor it by dividing it out or find out what the factors are. I'm kind of old school. I learned how to do this with long division, and that tends to be my go-to, but I'm going to do synthetic division today just because it's quicker. So just as a quick reminder, we're just going to draw this little, I don't even know what you want to call it. We're going to draw these lines. We're going to say, okay, what are the terms? What are my coefficients? Well, I have a 2. And I have, now, this is where we have to remember, I have a 2. That's attached to the x squared. I don't have just x by itself, but I still have to include it when I'm doing this division, which means I'm actually going to put a 0 as a placeholder. So that would be 2x squared plus 0x minus 1 is really what we're dealing with. And then I have a -1 all by itself. Now, what am I dividing it by? Well, that's where I'm going to take a look at this x plus 1 equals 0. So I'm dividing it by -1. I'm going to bring that 2 down. 1 times 2, a -1 times 2 is -2. 0 plus -2 is -2. And -1 times -2 gives me +2. -1 plus 2 leaves me with a 1 on the end. I have a remainder, so it didn't factor fully, but that's okay because I'm not overly concerned about what's happening there. So now let's go back in and fill the rest of this all in. So I have 2. X squared divided by x just leaves me with x, so I have 2x. Now I have a -2. X divided by x, this is just a -2. And then I have my plus 1 remainder on the end. And remember, I can't really do anything with that, so I'm going to leave it as 1 divided by x plus 1. Okay, so now we have this 2x minus 2, and that's actually the part that we're interested in because that's going to be our oblique asymptote. Our oblique asymptote is going to be when y equals 2x minus 2. So now we want to think about the limits approaching these oblique asymptotes as what's happening as they approach positive and negative infinity. So my limit as x approaches, let's do positive infinity first, and I think we can see that this x is going to get bigger and bigger and bigger and bigger and bigger. So we could say that f at x is going to be greater than 2x minus 2. Therefore, it's going to be from above. So it's going to approach this asymptote from above it. When I say f at x is greater than 2x minus 2, what I really am meaning to say there is that it's greater than 0. So it's going to be approaching it from above. Now my limit as x approaches negative infinity going the other way, so as this x gets, if we plug in values getting negatively bigger. I don't really know how to state that any other way than saying negatively bigger. We're getting really, really big negative numbers in there. Then we are definitely going to be less than 0 there, which means that this will be approaching from below. Okay, so now we have enough information to sketch the end behavior. So let's go ahead and do that. And I'm just going to blow this up a little bit. Let's get this drawn in here. So what do we know? Well, I know I have a vertical asymptote where x equals -1. So let's get that drawn in there. So there is my vertical asymptote where x equals -1. And now I have this oblique asymptote. And I have this oblique asymptote where y is equal to 2x minus 2. It's a straight line. This is going to give us the slope and our y-intercept for this straight line. So we actually can get this in the right spot. So I know that it's crossing the axis at -2, and it goes up 2 and over 2 because my slope is 2. So I am going to, we're going to have an oblique asymptote here. So my oblique asymptote is where y equals 2x minus 2. And that's what we've got going on. And just as a reminder, this is my slope. It's just a straight line. And this is my b value, or my intercept, where it crosses. So now let's start getting some of this on here. So we have our limit. Let's do that in blue. Okay, so we have this limit as x is approaching -1 from the left-hand side. So we're approaching it from this left-hand side. So we are coming at it from this direction. And as we're coming at it from this direction, it is going to go down towards negative infinity. So now let's get this out of there, not to confuse things. So now as we're approaching it though from the right-hand side, so now as we're coming at -1 from this direction, we know from this that we are approaching positive infinity. So it's going to be going up like that. Now let's take a look at what's happening around our oblique asymptote. Well, as we're approaching positive infinity here, it's approaching this asymptote from above. And as we are getting closer and closer to negative infinity, it is coming at it from below. So we can see the end behaviors, and we know that it won't cross the asymptote. So we could roughly sketch this in. And probably guesstimate that it's going to look roughly something like that. But to sketch it more accurately, we need to know the critical points. And we've done this before by using the first derivative test. We know how to use the power rule. I know you've seen how to use the power rule for a rational function, but it's not always easy to do that. You have to remember it's to the power of -1, then you're subtracting 1. So in this lesson, what I'm going to show you how to do is give you the rule to live by, which is the quotient rule, which is really going to make things a little bit easier. I'd be lying a little bit if I said it was going to make your life completely carefree and easy, but it will make it easier. And we're going to take a look at an example here in a second. Okay, let's determine the derivative of y equals 1 over x using the definition of the derivative for limits. It's been a bit since we've done this, so I'm going to walk you through it. Okay, so just as a reminder, if we are using limits to determine this, then our derivative, our first derivative, will be equal to the limit as h approaches 0 of f(x plus h) minus f at x all over whatever that distance of h is that it's moved. So my limit as h approaches 0 is, so f at x plus h in this case is going to be 1 over x plus h minus 1 over x all over h. Now, to subtract these, we need a common denominator, which means we need to do some mathematical gymnastics here to make sure we've got a common denominator. So, when we go ahead and get our common denominator, we are left with x minus x plus h all over x plus h times 1 over h. I'm just going to work this out on the right-hand side for you just so you can see what I've done. So we have 1 over x plus h minus 1 over x. Well, I need to multiply this term, both the top and the bottom, by x plus h, and I need to multiply this term by x, both on the top and the bottom. When the dust settles with that, I've started saying that again. Sorry, guys. X minus x plus h over x times x plus h all over h. Now, I want to get rid of a little bit of what's happening here, specifically that h on the bottom. So I'm going to multiply by 1 over h. That leaves me with x minus x plus h all over h times x plus h. We can eliminate some things from here. These two x's eliminate each other. I'm not, okay. I'm going to do one more step in here and then I'll show you. So now we're left with h over h times x plus h. Well, now I can eliminate these h's, and that becomes just 1, which is a little bit easier to work with. So now let's come back to our regularly scheduled program over here. And that is going to leave me with x minus x plus h all over x times x plus h times 1 over h. We are going to get rid of a little bit more here. The limit as h approaches 0. We have x minus x plus h. And I know I just showed you this on the other side, but I just want to make sure I don't lose track of anything here. X plus h. So the limit as h approaches 0. So these are going to eliminate, these two x's. We know these h's are going to become 1. We have this negative that we can't really forget about, though, because really we did have to multiply that out. So we are left with negative 1 over x. Whoops. Oh, I'm not going to put it like that. Hold on. Let me get rid of that. We are left with negative 1 over x times x plus h. Okay. So as h approaches 0, so we're going to plug in 0 here for each of our h values, of which there is only 1. So what are we left with? Well, we are left with negative 1 over x squared. That's a lot of work to get there. So what if I didn't want to do it using limits? What if I wanted to cheat a little bit and I wanted to use one of my rules to live by? Because we know them. We have one that we could use for this. So we could use the product rule. So if we wanted to cheat a little bit and not do what I was asking in the question, or if we wanted to double check our answer, let's go with that. Let's say we're going to double check our answer. So we have y equals 1 over x. Well, remember, anytime we have 1 over anything, we really can say then that that's 1x raised to the power of -1. I know how to use the power rule to solve this. I bring down the power, multiply it by the constant in front, and then subtract 1 from my power. So my derivative of 1 over x then could simply be equal to -1 times x to the raised to the power of -2. We could rewrite that as -1 over x squared. Same as what we got before. So this way is using limits. This way is using our power rule. So now what if our rational function is a little more complex than just 1 over x? Well, we can go ahead and we can tackle one of these the long way round by using our product rule, by rewriting what we have going on here. Because remember, I can rewrite this by saying y equals x minus 1 times x plus 1 to the -1. Those two things mean the same thing. So our long way, I'm going to make this bigger because I'm going to need more room. So our long way is going to be to use the product rule. And just as a reminder, our product rule, we have the derivative of the first times the second plus the derivative of the second times the first. And we have to use that special rule, chain rule, because we've got a product inside. So here's what we have going on. So I have x minus 1, and then in a bigger bracket here, I'm going to have x plus 1 to the -1. And just to help simplify this a little bit, I'm going to label these, and I'm going to call this part G and this part F, just to keep things straight a little bit. And I'm going to remind us over here that our first derivative is equal to the derivative of the first times the second. So the derivative of this times this in its entirety, plus my derivative of my second, this one, times my first just as it's written there. Okay, so it's been a bit since we've done one of these. I'm going to show you, just remind you again. So this is how I like to organize this. It just helps me keep straight what's G, what's F, what's the derivative of everything. So we have G, and G is just x minus 1. Just this, just as it's written. The derivative of that, so x minus 1, the derivative of x minus 1, well, that's just 1. The constant disappears, the -1 disappears, and the derivative of x is just 1. My f value is all of this right here, so x plus 1 to the -1. Now, my derivative of this is going to be -1, because I'm bringing this power down to in front. I'm bringing the power down to in front, so -1 times x plus 1. -1 minus 1 gives me now to the power of -2. And then remember, I have to multiply that by what's on the inside, the derivative of what's on the inside. And the derivative of what's on the inside in this case is just 1. So now when I go to put this together in my product rule, I'm going to have my G prime times my F and my G times my F prime. So y prime is going to equal G prime, which is just 1, times F, which is x plus 1 to the -1, plus, now I have my F prime times G. I'm going to write it slightly differently, and I'm going to put my G in front, x minus 1. And then I have -1 times x plus 1 to the negative 2. I have dropped this negative 1. I haven't really dropped it because what I've done is I've multiplied it by negative 1, so I don't have to keep writing it. So now let's clean this up a little bit. So remember, if this is to the negative 1, this is the same as saying this is 1 over x plus 1. We're going to do the same thing to this side. So now I have, and I have to multiply it through. So I have negative 1 times x minus 1 all over x plus 1 squared. Okay, can't add them together unless I have a common denominator. So let's get a common denominator of x plus 1 squared. I can do that by multiplying this first set of terms by x plus 1, both the top and the bottom. So there is that. And that will make this x plus 1 squared. So that leaves me with x plus 1. So x plus 1 times 1 is x plus 1. Then I have negative 1 plus negative 1x plus 1. So this becomes minus x plus 1 all over x plus 1 squared. I have x minus x. That gets rid of those. And that leaves me with 1 plus 1 on top. That leaves me with 2 over x plus 1 squared. My derivative, all the way back up here, the derivative of y equals x minus 1 divided by x plus 1 is going to be 2 over x plus 1 squared. Now, the other way that we could do this would be to do long division or synthetic division. You do you. I did one using synthetic division. I'm going to do this one using long division just because why not? Okay, so the other way that we could tackle this could be by using some long division and simply divide them out and then take the derivative. So just as a reminder, if you're doing long division, this is how I remember it. You're going to divide, multiply, and then subtract. Again, you could use synthetic division for this if you wanted to. So, what am I dividing out? I have x minus 1 being divided by x plus 1. So, if I'm dividing this out, well, x goes into x one time. I'm going to multiply. What do I have to multiply x by to make it 1x? Well, I just have to multiply it by 1. So I end up with x plus 1 here. That's times 1. And now I'm going to subtract. So there was my divide. There's my divide. There's my multiply here, even though it's just a 1 that I'm multiplying by. And then I'm going to subtract the whole thing. So x minus x is 0. Negative 1 minus 1 becomes negative 2. This negative 2 is just my remainder. So what am I left with? Well, I am left with negative 2 all over x plus 1 because I couldn't do anything with that, plus 1. Or you could say 1 plus negative 2, or 1 minus negative 2 over x plus 1. But I wrote it kind of this way on purpose. So now let's rewrite this so we can take the derivative of it using the power rule. So we have negative 2 times x plus 1 to the negative 1. That's just this rewritten as a negative power. Okay, that's just that rewritten as a negative power. Plus 1. Well, now I know how to take the derivative of this. So my derivative will be negative 1 times negative 2 becomes positive 2. X plus 1 to the negative 2 times 1 on the inside. I haven't shown that step. And my derivative of 1 is 0. Remember the constant rule. So what does my derivative end up being? I don't know if this way was any faster or not. We end up with 2 over x plus 1 squared. The good news is I'm going to show you a rule that's going to help you do this without having to move things around and make things negative and then put things back on the bottom. Finally, we have gotten to this actual rule that I am going to have you add to your rules to live by. So our whole goal for today was to get so that you could take the derivative of a rational function, either with using it or without using the quotient rule. But I think you will find that this might be a little bit helpful. So determine the derivative of h at x if it equals f at x over g at x. And this f at x, g at x, these are just two different functions, one being divided by the other, the same as what we've been seeing. So h at x is equal to f at x all over g at x. So we could rewrite this, and we could rewrite it as the product rule. So f at x, so this would equal f at x times g at x to the -1. Means the same thing. I haven't done anything different here. Haven't changed it numerically or mathematically. Now let's use our product rule. So I am going to end up with -g x to the -2 times g to the power of 1 times f. So this is my derivative. This is my derivative of this times this plus g to the -1, just my g value here, times my derivative of f. I end up with f prime g over g squared plus f prime at g. Now, I need to get a common denominator to add these together. So I am going to multiply this by g on the top and g on the bottom. And we are going to end up with g times the derivative of f minus f times the derivative of g all over g squared. This is our derivative, our first derivative, and this is our quotient rule. So our quotient rule can be rewritten, and I really haven't left myself enough room here, but let's write it over here. Let's write it in a different color just so it doesn't get lost in the shuffle here. I don't want to use green. Let's use a darker blue. So here is our quotient rule written out just in the way we do. So my derivative, my first derivative, when I have two polynomials, one divided by the other, is going to be equal to the bottom times derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now, my in-person class hates when I teach them this, but this is how I remember this. So we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. This is how I remember it. We take the low times the d of the high minus the high times the d of the low all over low, low. So low d high minus high d low all over low, low. And I'm going to write it down for you so you can remember it. So we have low d high. So we have our bottom times the derivative of our top minus high d low. Minus high d low. So this is our top times the derivative of our bottom. And then that's all over low, low. So high d low minus high d low all over low, low. Your new rule to live by. Let's put our new rule to the test. So our quotient rule allows us to differentiate polynomials somewhat more easily than using the power rule. Somewhat. Some of you may not like it, but it does allow us to differentiate it. And I personally do think it's a little bit easier. So let's put it to the test. So we have this rational function. We have 5 divided by x minus 2 cubed. So let's call this top is our f, the bottom is our g. Remember, we want low d high minus high d low all over low low. So let's start by writing out what we've got. So on the top, I have just 5. My derivative of 5 on the top is 0, using the constant rule. On the bottom, I have x minus 2 cubed. My derivative of x minus 2 cubed is going to be, I'm going to use that special power rule. Not really special power rule, just power rule. I'm going to bring the 3 down. I have x minus 2. Now I have 3 take away 1, so that becomes x minus 2 squared. All times the derivative of what's inside, that's just 1. So my derivative of the bottom is 3 times x minus 2 squared. Now we're going to apply that quotient rule. And just as a reminder, our quotient rule is low d high minus high d low all over low low, or the bottom squared. Okay, so here we go. Our derivative is going to be low d high. So my low is x minus 2 cubed times the derivative of my top, which is 0, minus my top, which is 5, times my derivative of the bottom, which was 3 times x minus 2 squared, all over my bottom squared. So we have x minus 2 to the power of 6. Just as a reminder, the product, or when we're doing exponents, if I have x minus 2 cubed and I'm squaring that, remember, I'm multiplying those. So it becomes x minus 2 to the power of 6. Okay, so now let's see what we can eliminate out of here, because there are some things. Anything times 0 is just 0. We can get rid of that. Now I'm going to multiply this out to get rid of this bracket. And I also can get rid of an x minus 2. In fact, I can get rid of 2 of them. So I can cross that out completely and drop that down by 2 of them to give me 4. So now what am I left with once we've done the math? Well, I'm left with negative 5 times 3, which is negative 15 on the top, and on the bottom, I am left with x minus 2 to the power of 4. That's how we use the quotient rule to find the first derivative of a rational function. Okay, let's look at one more example. So we're going to use the quotient rule for this one. I'm going to write it down again for you. So we know that the derivative of any two functions, one divided by the other, is going to be equal to low times the derivative of the high minus the high times the derivative of the low, all over the low low, or the bottom squared. I want to caution you here that the order of these does actually matter. When we're doing the product rule, it really doesn't matter because we're adding them. But when we're doing the quotient rule, the order does matter, and we do need to remember, because we're subtracting, that order matters. Okay, so let's take a look at this one. So we have a lot going on with this one. The very first thing that we're going to do is we're going to go ahead and simplify it to take the derivatives, and then we're going to break it back out in order to be able to do our quotient rules. So when we expand this out, so I'm going to distribute, I end up with x squared minus x on the top, and on the bottom, if we FOIL this on the bottom, we end up with x squared plus 5x plus 6. Now remember, this is just an in-between step. I'm only doing this so that I can get my g prime, so I can get my first derivative of my bottom value or my bottom polynomial. But when I go to use my quotient rule, I actually am going to put them back into this factored form. Okay, so let's break this down. So we have, what is our f? Well, our f is x squared minus x. The derivative of that will be 2x minus 1. On the bottom, I have x squared plus 5x plus 6. My derivative of that will be 2x plus 5. Okay, now that we have that all sorted out, let's go back and use our quotient rule to determine this. So I have low d high. So my bottom, which is just my x squared plus 5x plus 6, x squared plus 5x plus 6, times the derivative of my top, which was 2x minus 1, minus, I feel like we should have some more brackets around that there. Okay, that makes me feel a little better. And let's do the same thing over here. Now for this one, I have high d low. So I have my top, which was x squared minus x, times my derivative of my bottom, which was 2x plus 5. And again, feeling a little better about having that all contained. Now, for the bottom of this, we're going to go back to this because remember, it's the bottom squared. So rather than have to go back in and multiply that times itself, because we're going to end up probably eliminating a few things maybe before the dust all settles. So I have x plus 2 squared and x plus 3 squared. That's just my bottoms squared. And I just realized I said when the dust settles again. Okay, but try not to do it anymore. Okay, so now we're going to FOIL like our life depends on it. We are going to FOIL, FOIL, FOIL. So FOIL, FOIL, FOIL to get these bad boys back out into something that we can collect the like terms. So here we go. So we have 2x times x squared, 2x times 5x, 2x times 6, and then we're going to do the same thing, different color, -1 times x. You get the drill. And then we're going to do the same thing with this one. I'm going to go ahead and do it. So we end up with 2x cubed plus 10x squared plus 12x minus x squared minus 5x minus 6 minus 2x cubed plus 5x squared plus 2x squared plus 5x. Whew! All over x plus 2 squared, x plus 3 squared. And we're just going to leave that bottom alone. Now, if you want to know why we spent so much time in grade 9 and grade 10 teaching you how to collect like terms, this right here is exactly the reason why. So let's start looking and see if there's things that we can collect these like terms. So I have a 2x cubed minus a 2x cubed. Those eliminate each other. 10x squared I'm going to leave alone. 12x minus x squared. Okay, so I have a 10x squared minus x squared plus 5x squared plus 2x squared. So that leaves me with 16x squared. Then I have some x's that I need to figure out. So I've got a 12x, a minus 5x, and a plus 5x. Well, that plus and minus, those eliminate each other. So really what I'm left with there is a plus 12x. Plus 12x. And now let's look for any numbers just by themselves. And the only number that I have by itself is this minus 6. So that's going to come there. All over x plus 2 squared, x plus 3 squared. Now, we could factor the top out and see if we could eliminate, but for right now, we're just going to leave it like this. Okay, here's another one for you. I'd like you to pause the video, write this one down, see if you can work your way through the product rule to solve this one. So low D high minus high D low all over low low. Pause the video, see what you get for an answer, and come back once you've done that to see what the solution actually is. Okay. So hopefully you've given it a try. Let's break it down like we have been doing. So my top is F, my bottom is G. That's just how I'm keeping it straight. So my top is going to be x squared plus 2x plus 1. My derivative of that is 2x plus 2. Power rule again, constant rule is 0. On the bottom, I just have x, and my derivative of x is just 1. Okay, so now let's put it together. Low D high, probably should write this out a little bit more formally than what I have been doing. Okay, so my first derivative is, I have my bottom times the derivative of my top. So my bottom is x times the derivative of my top, which is 2x plus 2. And we're going to put them in a little safety net of some brackets. Minus, again, those safety net brackets, my top times the derivative of my bottom. So my top is x squared plus 2x plus 1 times the derivative of the bottom, which is just 1, all over my bottom squared. Well, that one was easy. That's just x squared. Okay, so now we are going to FOIL to expand everything out. So once we have expanded everything out, we get, so x times 2x, we get 2x squared plus 2x minus x squared minus 2x minus 1 all over x squared. Let's collect some like terms. So I have 2x squared minus x squared. That leaves me with just x squared. I have a 2x, a plus 2x, and a minus 2x. They eliminate each other. And then for numbers, I just have this lonely little 1 on the end. So this becomes minus 1. So x squared minus 1 on the top, all over x squared. Now, if I want to put this in proper form, I'm going to go ahead and I'm going to factor out the top. So we have x minus 1, x plus 1, all over x squared. And that is where we will leave that 1. So our derivative is x minus 1, x plus 1, all over x squared. Now we're going to use our quotient rule to be able to find the first derivative, which is going to allow us to find all of the critical points or critical point for this particular function, y equals x over x minus 2 squared. So if you remember, to find the critical points, we take the first derivative and then set that first derivative to equal 0. So let's use our new quotient rule. Which tells me that the first derivative is equal to low d high minus high d low all over low low or low squared. So if my original function is y equals x over x minus 2 squared, I'm going to do a little bit of the legwork right now. My top will be the f function, my bottom will be the g. So f is equal to x. My derivative of x is just 1. G, or on the bottom, is equal to x minus 2 squared. And my derivative of x minus 2 squared is 2x minus 2. That's it. So now we can plug it all in to determine our first derivative. I'm going to make that a little smaller just so I have a little more room here. Okay. So my first derivative will be equal to, so remember, we're looking up here and we're saying, so my first part is low d high. So my low is my x minus 2 squared times the derivative of my top, which is just equal to 1, minus my top times my derivative of my bottom. So the top is just x, and the derivative of the bottom is 2x minus 2. And all of that will be divided by the bottom squared. And on the bottom, we have x minus 2 squared. And we are going to square that. So now let's expand and simplify and see what we end up with. So if I'm going to expand and simplify this first part, really I'm just getting rid of that 1. So we are left with x minus, let's get it in red here so we're all in the same color. So we have x minus 2 squared. Now let's look at this second part and let's expand this out and simplify it. So I have x times 2, and there's a negative there. So that gives me negative 2x times x minus 2. Using my exponent rules, I know a power to a power will be x minus 2 to the power of 4. So now let's see if we can pull out any common factors. So I'm looking for a greatest common factor. And I can indeed pull out an x minus 2 as a common factor. Now, there's a couple of different ways you could do this. If you're brave and you can keep track of things, you could go ahead and just say, okay, I can take 1 out of the bottom. That leaves me with 3. That eliminates that, and that also will eliminate one of those. However, if we end up getting that mixed up a little bit, we can end up making a mistake. So I think it is better just to go ahead and pull it out and do it properly. So we are going to pull out an x minus 2, and that leaves us on the top with x minus 2 minus 2x. And then on the bottom, we have our x minus 2 to the power of 4. Now I can comfortably go ahead and make sure that I'm not going to make any mistakes by eliminating that and eliminating one of those. So that leaves us with a derivative of x minus 2 minus 2x all over x minus 2 to the power of 3. Now, we can still go ahead and we can simplify this a little bit, and that leaves us with negative x minus 2 all over x minus 2 to the power of 3. So now we have our derivative. We can go ahead and we can use this derivative to determine our critical points. So let's determine our critical points. Let's do this over here. So just as a reminder, we want to set the first derivative equal to 0, kind of like we're factoring it. We kind of are. Well, not really factoring it, I guess. We're breaking it down. We're making it equal 0. So we have 0 is equal to negative x minus 2 all over x minus 2 cubed. Okay, so I can go ahead now and isolate for x. So I am going to multiply both sides by x minus 2 to the power of 3. That will eliminate that on this side, and 0 times anything is just 0, so that also eliminates it on that side. So now I'm left with 0 equals negative x minus 2. I'm going to move this x over here, so x is equal to negative 2. There is my critical point. I have a critical point where x equals negative 2. Not really sure what that was. I think my cat just fell off the table. Okay, so now we know that this is a critical point. We're going to plug this point into our original function. So plug into f at x to determine the coordinate for this. And when we do that, when we plug -2 into y equals x over x minus 2 squared, we end up getting a critical point of -2 and -1/8. And that's going to be our critical point for this particular function. Here are the homework questions for this particular section, and there is also an exit ticket for today posted to the VLE.